Assalamualaikum to Dr. Azian Azamimi Abdullah. My name is Alia Sulaiman Mazlan. I would like to present my opinion based on question number 4. I'm going to start my presentation about its Maglev trains with a bit of the history of Maglev trains. So, Maglev trains are derived from the term magnetic levitation. It is train without wheels. Instead of rolling along the track, it quietly float above and glide smoothly from origin to destination without even touching a rail. So, the fundamental idea behind maglev technology can be traced back to the early 20th century. Much work went into laying the groundwork for these trains, including the development of electric motor and research in magnetism. At this time, Germany and Japan began researching the potential of maglev. Japan continued development of its maglev technology in the 90s and beyond. No commercial line have been established in the country, but they are still carrying out research. In Germany, a commercial transrapid line connecting Berlin and Hamburg was proposed in 1992. Not all was lost though, as the Chinese took notice and commissioned the German to build a transrapid train in Shanghai, while the Shanghai Maglev, which resulted from this venture, is now the only high-speed maglev train in the commercial use. So I'm going to continue my presentation with how does this maglev train work. So basically, maglev trains do not have wheels or rails, as we know, and as shown in the figure 1, they have a guideway and they float down this guideway without ever touching them. So figure 1 shown the comparison of the normal wheel rails versus the guideway. And next, based on the figure 2, there are 3 essential parts to achieve this maglev functionality, and that's it: levitation, propulsion, and the guidance. So first, we're going to continue to talk about the levitation. So levitation is the ability for the train to stay suspended above the track. There are 2 important types of levitation technology. So we're going to start with the electromagnetic suspension, or known as EMS. EMS uses the attractive force of electromagnet placed on the guideway and on the train to achieve levitation. The benefit of this method are that it is simpler to implement than electrodynamic suspension, or known as EDS, and that is maintain levitation at zero speed. But the drawbacks of this system are inherently unstable. At high speed, it becomes difficult to maintain the correct distance between trains and the guideway. If this distance cannot be kept, the train will fail to levitate and come grinding to a halt. So that's why EMS requires a complex feedback control system to ensure the train is always stable, while EDS, or electrodynamic suspension, use the repulsive force of superconducting magnet placed on the guideway and on the train to achieve levitation. The magnet move past each other while the train is running and generate the repulsive force. The benefit of this method are that it is incredibly stable at a high speed, and maintaining correct distance between the train and guideway will not be a concern. But the drawbacks are that sufficient speed needs to be built up in order for the train to levitate. Additionally, the system is much more complex and costly to implement. So next is the propulsion. So propulsion is basically the force that drives the train forward. And next, lastly, is the guidance. So guidance is what keeps the train center over the guideway. For high-speed magnetic levitating trains, repulsive magnetic force are used to achieve this base, like in the figure shown, and it's a comparison between the transrapid guidance and MLS guidance. So based on the transrapid, there are two electromagnetic rails placed on the train facing either side of the guideway, while this rail keeps the train from moving too far, while in the MLS, guidance is coupled with the levitation system. The levitation rails on the either side of the train are connected to each other. Through this connection, when the train moves closer to one side, a restoring force induced which push it back toward the center. Thus, the MLS is both levitated and guided at the same time. And lastly is about proposing. So I would like to propose linear motor as the suitable electrical motor and drive that can be used in the magnetic levitating trains. So why? Linear motor electric induction motor that produce motion in a straight line rather than rotational motor. Rotational motion, sorry. In a traditional electrical motor, the rotating part, as you can see on the figure, spin inside the stator, the static part. But in a linear motor, the stator is unwrapped and laid out flat, and the rotor moves past it in a straight line. So linear motor often use superconducting magnet, which are cooled to low temperature to reduce power consumption. And to explain more about a linear motor is effectively an AC induction motor that has been cut open and unwrapped. The stator is laid out in the form of a track of flat coils made from aluminium or maybe copper and is known as the primary of the linear motor, while the rotor takes the form of a moving platform known as the secondary. So when the current is switched on, the secondary glide past the primary supported and propelled by the magnetic field. And from my opinion, the advantage of using linear motor are as the platform right above the track on a cushion of air, there's no loss of energy to friction or vibration. And next is the lack of intermediate gearbox to convert rotational motion into straight line motion, and this could save the energy. And finally, as both acceleration and braking are achieved through electromagnetism, linear motor are much quieter than ordinary motor. Well, and that's all from me. Thank you.